Good morning, class. This is your lecture video for today's chemistry assignment. If you're watching the video, I assume you already know that we have a chemistry assignment. But if you don't know, we will have an assignment every single day that we are not here at school. And so make sure that you're getting on Google Classroom and make sure you're getting on Sapling to see what the assignment is and start working on it. And if you have any questions, please let me know. The earlier, the better. If you wait until 9 or 10 o'clock to do your assignment and you have questions and email me, I'm likely not going to be able to email back until the next day. And then you didn't get your assignment completed. And that's going to start to pile up on you. So make sure that you get started on these assignments quickly. And if you have any questions, please send me an email and I will get back to you with the help that you need or possibly send you another video to kind of help you out with that problem. So today, we're starting on a new chapter. We're starting with stoichiometry. Specifically, we're going to start to talk about the mole. And the mole is a very unique number in stoichiometry. It lets us count a lot of really, really small things that normally would not be countable, like atoms in a pen or atoms in a board. And so that's a lot of atoms, and it's a really, really huge number. And so we're going to look at the number today. We're going to talk about how we use it and how we figured that out. And this is going to be the setup for stoichiometry and the more difficult problems that we have. Today shouldn't be too difficult. I looked at some of the questions on the Sapling assignment, but you are going to want to pay attention to the video and make sure that you understand the concepts behind this. So where we're going to start off with is the mole. The mole itself is just a way of measuring things. It's just a number. In the same way that a dozen is a number, how many is a dozen? So I think you all know what a dozen is. And you can have a dozen of anything. The most common things that we talked about are like a dozen roses or a dozen donuts. You can have a dozen students. If you're rich, I guess, you can have a dozen cars. Or if you own a car dealership, you can have a dozen cars. There are more than a dozen desks in my room. You can have a dozen of a lot of things. It's just a number, and you can apply that number to literally anything. And so the same thing works with a mole. It's just a much larger number. The number for a mole is 6.022 times 10 to the 23rd. I did list an extra 2 here. I'd like you to try to use that number and try to remember it as 6.022. Sapling only gives you the 6.02 times 10 to the 23rd, but you get a little bit better answers if you use that second 2. So let's come over here and take a look at how big this number is very quickly. It kind of gives you an appreciation for how many we're talking about here. So the number is Avogadro's number, or the number for a mole. And we'll get into Avogadro in a little bit. Avogadro. This number is 6.022 times 10 to the 23rd power. This is a very, very large number, and I want to show you how large this number is. If I take my 6.022 and I need to move the decimal place, how many times? 23 times. That's a lot of times to move it. So watch how big this number gets very quickly. So I'm going to move it 1, 2, 3. And then I'm going to have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and then put my decimal place back. I will erase the decimal here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's it. So 6.022 times 10 to the 23rd power turns into this number. If I start to add some commas, we can figure out just how big this number is. So there's a comma for 1,000. There's a comma for 1,000,000. There's a comma for 1,000,000,000. There's a comma for 1,000,000,000,000, a quadrillion, a pentillion, and then a sextillion. I guess those are the numbers for them. I think they are. But yeah, so let's just show you. This is 1,000. This is 1,000,000. And then it keeps going. So I guess I can put a comma there. That would be a billion. That would be a trillion. So you're talking what? Another 1,000, million, billion, 602 billion trillion. 602. I believe this is sextillion or 602 billion trillions. It's a really big number. It's an extremely big number that is very difficult to deal with. And the truth is, if you're having to do math with this number, which is what this entire chapter is going to be about, us doing math with the mole number or Avogadro's number, you don't want to have to put this into your calculator every single time. That's a lot of zeros. That's a lot of typing. And so it's much, much easier to use it in scientific notation. In order to use it in scientific notation, you have to get used to multiplying and dividing in scientific notation. And so today we're going to go over some of those steps. We're going to talk about the number itself, and hopefully we will be able to go through the assignment fairly easily. So if we come back to the PowerPoint here, we have mole, and a mole is just a unit of measurement. It's equal to approximately 6.02 times 10 to the 23rd particle. And this number is also called Avogadro's number, after the gentleman who discovered it, Amadeo Avogadro. I think his name's actually longer than that. Maybe we'll look it up and watch a little video about Avogadro. But Avogadro's number is 6.022 times 10 to the 23rd. And he's the one who discovered that if he took 12 grams of carbon-12, that this is the number of atoms that he would have in 12 grams of carbon-12, approximately. Close enough that the math works out for other elements as well. And so the idea here is you take the periodic table, you find the weight of the element that you're looking at for the atomic weight. So carbon weighs roughly 12 atomic mass units, AMUs. If he had 12 grams of the carbon that weighs 12 atomic mass units, how many atoms would he have? You can't count atoms. We can't separate atoms, put them on a table and count them like pennies. They're much too small. And so what we need is a mathematical way where we can start to count atoms. And that's what Avogadro's number lets us do. So if we do math with Avogadro's number, we can figure out how many atoms we have, how many molecules we have in a certain weight, like 12 grams, of a certain chemical, like carbon-12. And so this is very, very useful. So what we're measuring here normally with Avogadro's number, like I said, just like a dozen, you can measure anything in Avogadro's number. But specifically what it works well for is really, really small things like atoms, molecules, formula units. So a actual molecule that fits a specific formula, ions, positive or negatively charged atoms or molecules, and then electrons. So we can count any of these things using Avogadro's number, and in fact you will. Know that if they say the word particle, they could be referring to any of those things: atoms, molecules, formula units, ions, or electrons. Those are all technically particles. Now, a mole is a unit based on a number of particles, not mass. So mole does not tell you how heavy something is. Mole tells you how many of something you have. So for instance, like if we relate this back to a dozen, if I have a dozen roses, that just tells me I have 12 roses. It doesn't tell me how heavy the thing is. I can also have a dozen bricks, and the bricks are going to weigh a lot more than the roses are. I still have the same number of them, but when I'm weighing different things, I should have different weights. And so remember that the mole is not a unit of weight. It's a number. It's just a count of how many things you have. So there are always 602 times 10 to the 23rd power particles in a mole. It doesn't matter what you're counting. If you have a mole of anything, there are 6.022 times 10 to the 23rd of those things inside that mole. In the same way, if I have a dozen of anything, I'm going to have 12. It doesn't matter what I have, what I'm talking about, a dozen's going to be 12. Little side note, I do this every year for my classes, so I might as well tell you. Has anybody heard of a baker's dozen? Do you know what a baker's dozen is? A baker's dozen is 13 and not 12. Because way back in the day, I think maybe like ancient Rome, they were really worried about bakers. Apparently, they were really worried about bakers ripping people off and charging them for 12 things and not giving them 12. And so for someone who sold food, like a baker, if you charge somebody for 12 and didn't give them 12, they would chop your hand off. And so in order to keep both of their hands, which are very important to your work, you just go ahead and give people 13. Because if they didn't get the 12, you didn't want to be in trouble. So you give them an extra one. That way you know they at least got 12. And so a baker's dozen is 13, and that's a nice little piece of strange history for you, as long as we're talking about numbers. So what you see here in this picture is 4 different chemicals, all of which are 1 mole. So this is 1 mole of sucrose, which is sugar, 1 mole of sugar, 1 mole of water right here. It's hard to tell exactly where it's filled up with. I think it's filled up right here to like the maybe 18 milliliters mark. 1 mole of aluminum foil, which looks like a lot of aluminum foil, but there's a lot of empty air in there. And then 1 mole of sodium chloride, which is salt. So note that 1 mole of sugar and 1 mole of salt are a lot different. Sugar molecules apparently are much, much bigger and weigh a lot more than salt molecules, which are much, much smaller and weigh a lot less. And so all of these jars or containers here have 1 mole of the substance inside of them, 6.02 times 10 to the 23rd particle. Even though they all have different weights and different volumes, it's the same count of atoms inside each of those beakers. Now, molar mass. What is a molar mass? A molar mass is the mass of 1 mole. Mass is a weight. It's an amount that we equate to weight here. And so molar mass, if I have 1 mole, how many grams is that going to be? How much weight is that going to take up? So the mass of 1 mole of a pure substance, the units are in grams per 1 mole. The molar mass of an element is numerically equal to its atomic mass. And this is very important and very easy. Go to your periodic table. At the bottom of each of the squares on the periodic table, you should see the atomic mass. If you're not sure exactly where the atomic mass is on your periodic table, just look for the key. Here on ours, the key's right here in the top center, and it tells us the atomic mass is the bottom number there. And so, for instance, the atomic mass for carbon is 12.011. 12.011. So if I have 1 mole of carbon, it should weigh 12.011 grams. That is the weight in grams for 1 mole. If I just have 1 atom of carbon, it's the atomic mass, it will weigh 12.011 atomic mass units. So that's how we measure really, really small things. But if you're measuring a mole of something, which is a really big number, you want to go to grams. It's going to be the same numerical number. It's just going to have a different unit on it. So here's their example. Strontium on the periodic table, Sr, which is over here to the left in my alkali earth metals. It weighs 87.62 atomic mass units for 1 atom of strontium. But what if I have a mole of strontium? What if I have 6.022 times 10 to the 23rd atoms, which is, if you remember over there on the board, 602 sextillion atoms. If I have that many atoms of strontium, it's going to weigh the same number. It's just going to be in grams instead of moles. So 87.62 grams of strontium for 1 mole. Now, determining the molar mass of substance with more than 1 element in them requires an understanding of the chemical formulas. You need to add up the atoms in the chemical formula to get a total, and that total is going to tell you how much that molecule weighs for 1 mole. So their example here is NH3. This is the chemical ammonium. And so NH3 has how many nitrogens? Just the one nitrogen. And how many hydrogens? It's H3 with a little subscript of 3. So you should have 3 hydrogens. So in order to figure out the weight of 1 mole of NH3, I need to add up the weights of each of these molecules. So I take the weight for nitrogen, which is 14.007, and I take the weight of hydrogen, which is 1.008, but I have 3 hydrogens, so I need to multiply that by 3 or add 3 of them together along with the 1 nitrogen. That should give me a total for that one formula. So let me actually do that real quick because they don't happen to do it in on the PowerPoint, and I will just do it up here in the corner. Nitrogen from my periodic table is 14.007. Nitrogen, well, my formula is NH3, so I have 1 nitrogen and 3 hydrogens. The nitrogen is 14.007, and each hydrogen is 1.008, and I'm going to times 3 on that. I'm going to add those together. And so 1.008 times 3 is actually 3.024. So I add 14.007 plus 3.024, and what I end up with is 17.031. And so how much does ammonium weigh as 1 mole? 17.031 grams per 1 mole. And all I did was I looked up the weight of my 1 nitrogen, I looked up the weight of hydrogen and multiplied it by 3, or just added 3 of those together. You can just add if you don't want to multiply. So 1 nitrogen plus 3 hydrogens added together equals 17.031. And my units are grams per mole because I have 1 mole of these, which means I have Avogadro's number of atoms of ammonia. So coming back over here, how do we determine the molar mass of substances with more than 1 element? You look for the subscripts. So you find out how many. Their example was NH3, and the little 3 comes after the H, and so I have 3 hydrogens and only 1 nitrogen. You're going to multiply the number that you have, the little number, by the amount of the weight for that element. So over here, I had 3 hydrogens. I took my little 3 from my NH3, and I multiplied the weight of the hydrogen by that 3. And so each hydrogen weighs 1.008 multiplied by 3 is equal to 3.024. That's what they're telling you to do here in the PowerPoint. So their example, they did another example, MgOH2. They have the parentheses around the O and the H, and then a 2 outside of that. So I have 1 magnesium, 2 oxygens, and 2 hydrogens. And I need to add all of those together to get the weight of that molecule. So they do another example here, formula mass. Magnesium bromide is the formula they're using. 1 magnesium, 2 bromines. You can see MgBr2 here. They have a total weight of 184.113. And how they got there is they have 1 magnesium and 2 bromines. They're going to add those together. So if you look on the periodic table, magnesium weighs 24.305. They have the same thing here. If you look on the periodic table, bromine weighs 79.904. And how many bromines do I have? I have 2 of them. So I multiply the 79.904 times 2, add 24.305, and my total should be 184 0.113. So they're saying the molar mass of the compound is numerically equal to the formula mass of that compound. So if I were to just add up the individual atoms of 1 magnesium and 2 bromines, I should get the exact same number. Just instead of atomic mass units, it's in grams per mole. Now, they have 3 steps for finding the molar mass. So step 1, you're going to determine the formula for the substance. I need a formula. If I don't have a formula, then I don't know what to add together. So step 1 is always find the formula. Sapling should give it to you. Step 2, for each element present, multiply the number of moles of that element shown in the formula by the molar mass of that element. So in the example that we did over here, we only have 1 nitrogen, so I don't have to multiply that by anything, but we did have 3 hydrogens. So I take the weight of my hydrogen, multiply it by 3, and get a total, which is 3 times the weight of just one of those. So that's step 2. And then step 3, find the sum. If we're getting a sum, what kind of math are we doing? We're adding. So find the sum of the products of step 2, add them all together, and that should be your total. They're going to do an example for us here. Find the molar mass of magnesium hydroxide. So that's the MgOH2. So you have to figure out the formula for this, or in Sapling, they'll probably give it to you. Here's our magnesium. Hydroxide has a hydrogen and an oxygen together, OH. And in order to make the charges equal out, because a magnesium is a +2 and a hydroxide is a -1, I need 2 hydroxides. So my formula is going to be MgOH in parentheses and then 2 outside. So how many atoms of each of these do I have? I have 1 magnesium, I have 2 oxygens, and I have 2 hydrogens. And so I need to add those together to find the molar mass. So step 2, take each of the elements and multiply by the number of moles shown. I only have 1 magnesium. So I have 1 magnesium. I'm going to multiply by the weight of that magnesium, which I find on the periodic table. So go to the periodic table. Magnesium is 24.305 grams per mole. So 24.305 grams per mole times 1 is still going to be 24.305 grams per mole. The oxygen and the hydrogen I'm multiplying by 2. So I take my 2 oxygens, multiply by the weight of 1 oxygen, which is 15.999. Take my 2 hydrogens, multiply by the weight of 1 hydrogen, which is 1.008. Multiply those out. And the oxygen now, instead of 15.999, weighs 31.998. And the hydrogen, which one of them weighs 1.0079, now weighs 2.0158. So simple math. These numbers aren't super easy, but the math is easy. I'm just taking the weight of magnesium, I'm taking the weight of oxygen times 2, and the weight of hydrogen times 2. And now, third step, I need to add all 3 of these numbers together. So I write all 3 of these down, and I'm just going to add them together. And the total that I get is the weight for this molecule. 1 magnesium, 2 oxygens, and 2 hydrogens. Add them all together, and that is my new weight, 58.319. So that is the sum of the molar mass, 1 mole of magnesium hydroxide. So I hope that makes sense and helps a little bit. I will post this video probably along with another video, maybe from Khan Academy or something, to try to explain it a little bit better. If you have any questions or need any help, please let me know. If it's a math problem, you can always send me a screenshot of your sapling problem so I can actually see the numbers that you're using. But please let me know if you need help. Send me an email. Good luck on this assignment. Have a great weekend, and we will pick up with another assignment tomorrow. Look at the empty classroom. No students. No students. So hope you're having fun at home and staying safe. Wear your masks. Stay inside. Don't go getting the COVID while we're gone for Christmas break. It's not going to be fun for you. So everybody have a nice day, and see you next week.